Today, first, we're going to finish our discussion about tools. So you guys remember, practical biophotonics, we have light sources, which we've covered. We have light tissue interactions. Tools, we've had now over 2 lectures. And we've had basic biology. So we're almost to the point now, after the first hour today, we'll be at the point where you guys have gotten a tour of all the basic pieces. And it'll be time to get into the specifics of certain types of projects in biophotonics. Okay? So, Biophotonics Tools. Let's refresh ourselves as what we did before. We had talked about the laser, how it could provide very precise quantities of photons, which could be used to manipulate, alter, and probe biological samples. What were some examples of how we use the laser to manipulate or alter biological samples?
You should use like laser tweezers to actually grab and move them into the cell.
Yep. Yep. Anything else? Let's see. Vaporized things. There you go. It's always a fun one. Can you use them to cut? Any common examples? You guys remember some of the common things you can do with them?
LASIK surgery.
LASIK surgery, which was what? What was LASIK surgery?
Oh, it was like they sliced like the top part of the eye, and then they like shoot like controlled bursts of photons into the cornea to like reshape it. So
Yes.
it focuses the light.
Yes, perfect, perfect. Okay, so you guys remembering that. Fiber optics. What was the big thing about fiber optics, other than you can bring light wherever you want? What do you guys remember about them?
You can bend it and it still conducts.
Okay. Yeah, that's the main thing about fiber optics. And do you guys remember why you can do that? Why can you bend a fiber optic? Let's see, anyone else?
Internal reflection.
Total internal reflection, yes. Okay, which means the light is kind of trapped inside this fiber and travels around corners and bends. The microscope. Microscope. You guys know what the microscope does. It lets you see very small things. What you may not be as aware of is the whole huge range of techniques in microscopy for seeing different things. And part of what you're going to do when you come this Wednesday to the Center for Biophotonics is you're going to be seeing the world's highest resolution commercial microscope. There's only, I think there's about, now there's like 4 or 5 of these in the world. We had the first one because we worked with the company to make it. So you'll be seeing that microscope. And I'll be telling you a little bit more about it later today. But you'll also be seeing much more basic microscopes. And you guys will get to use microscopes on your own sample. Okay? And we'll discuss the specifics of that. But my goal is for you guys to bring such interesting samples that will warrant making another poster, like we did last year. Okay? And we'll talk about the specifics of that a little bit later. The eye. You guys remember anything interesting about the eye? We have a blind spot. Okay. Anything else? We can't see infrared. Okay. We're limited in the range of wavelengths we can see. Any other things about the eye? Do you guys remember? Yes.
Like we can see green light the best.
We can see green light the best. Yeah. For an equal number of photons, we perceive green about 10 times better than we perceive blue. And somewhere on the order, 10 to 20 times more than blue, and on the order of about 10 times better than red. So for an equal number of photons, the green light will appear about 10 times brighter to us. Okay. Anything else about the eye? Do you guys remember what the sensors are in the eye?
There's rod and cone cells, they're called rods for black and white, and do a photo.
And anyone remember how many different types of cones we have? We have 3. And something I didn't tell you guys about, because I hadn't fully appreciated it before I went to my short course on the eye that Monday that I was gone, but the red and green are very, very close in their maxima, which they can absorb. And the prevailing thinking is that those used to be 1. We used to only have 2 color vision, something in the blue and something in the kind of orange yellow, kind of tuned to the sun, the maximum output of the sun. And then that one mutated into 2 that had slightly different absorption characteristics, so that we could now have what's called trichromate vision, so 3-color vision, because that was supposedly some kind of advantage for the the hominids that had that 3 versus the 2. Okay? So another thing, another tidbit that I wanted to share with you guys about vision is that as the light goes down quite a bit, as it gets darker, but not quite dark yet, you'll actually be able to see blue a lot better than you're able to see red. Okay? Which is kind of the funny thing. You wouldn't necessarily think that because blue in general, we have less sensitivity towards blue. But as the sun's going down, and it's, once the sun is down, maybe half an hour, 45 minutes after the sun has disappeared, take a look and you'll see someone wearing a red shirt. The red shirt will look blackish, but blue jeans will still look blue. Okay, so it's kind of, our sensitivity shifts towards the blue as the light goes down at night. Kind of interesting tidbit. Okay, so that's the eye. What we're going to focus on now are the CCD, which stands for Charged Coupled Device. And that's a device that, for example, makes your digital cameras work and makes them able to collect light information. And we're also going to talk about the spectrophotometer. You guys used a spectroscope before. Remember those NASA spectroscopes that we saw the little lines in? Well, this is the spectrophotometer. So this is a more precise way of getting light intensity information. It's called a spectrophotometer. Okay? So the spectrophotometer is what you guys will be using next week. Actually, yeah, you'll start using it next week and the week after. And that'll be the tool that you use to get the data for your second lab report. Okay? So the CCD. Simplest way to think about it is a solar cell. Okay? What does a solar cell do? Anyone know? What does a solar cell do? Any thoughts? Sorry? It gathers light. So what, you got a big light ball that you can, what do you guys think it does? What does it do with that?
Is it like what's in like solar panels to transfer light energy to other types of?
Yeah, what other energy do they, what's a photovoltaic do?
Use the energy from photons to produce photons.
Yeah, so basically what it does is the materials in there, the semiconductor materials in there are 2 different types, and you get something known as the photoelectric effect, which is if you get the right wavelengths of photons hitting this material, it transfers, remember how photons can excite electrons? Okay? Well, you get a transfer of electrons from one of these semiconductors to the other. So effectively you get a flow of electrons. And a flow of electrons is electricity. Okay? So effectively in a photovoltaic cell, I convert photons into a voltage. Okay? An actual flow of electrons. Okay? That's a current. A flow of electrons is a current, but I get a potential difference which gives me a voltage. And I can make it do something. Okay? Now, effectively, what a photodiode sensor is, photons hit a semiconducting material, creating free electrons that generate a measurable current. Okay? So a way to detect the amount of photons in a given sample of light is to have something that converts that into electricity. And then I can measure that current. And the amount of current that I have is directly proportional to the amount of photons that are hitting the surface. Okay? So this is in a sense, one of the simplest devices for determining specifics. Yes?
Where do you get the replacement electron? What does the electron need?
So it actually has to be a circuit, it has to flow. So the way that it works, you have to come across, but then there has to be a way to kind of bring it back. Okay? And in this case, the photons from the sun keep on exciting, and you do get a flow back, because you have to have a flow to actually get current. Okay? Current doesn't work in just one direction. So, you can do some tricks with this, where you can make something called a photo avalanche detector, which basically, make a long story short, you can make detectors like this that are very, very sensitive. Okay, they can be sensitive to 1 photon. And by a photomultiplier effect, you can multiply 1 photon into something that actually would be a measurable current. So our most advanced instruments that are trying to detect just 1, 2, 3 photons, or trying to detect it very quickly, will use a scheme like this. Our slightly less sensitive instruments will use something called a charge coupled device. This is really a photodiode array. So you're taking like those photodiodes that you saw before, but you're arranging them all in a row and all in columns, okay? Till you get, think of it as a grid of these things. And hence you get your 2 megapixel camera or 5 megapixel camera. What does that mean? Well, I'm going to use 6 because it's the easier one to think about. It means there's 3,000 of these going across by 2,000 of these going down. 3,000 times 2,000 equals 6,000,000 6 megapixels. Okay? Each one of those little things looks something like this. And it has a surface over which, not the whole thing, but a surface over which the incoming photons get converted into electricity. So for each one of those 6 million dots, I can figure out how many photons are hitting it. Does that make sense? So if I get more dots hitting it, it's a brighter pixel. If I get less dots hitting it, it's a darker pixel, which gets converted into electricity, and that electricity is red. That CCD array is scanned very, very quickly, leading to a picture that you guys have in your digital camera, or your digital phone, or any of those devices that take a picture. Okay? Now, does that lead to color? All I'm measuring is the amount of photons. It leads you to a black and white image. Okay? An array like that would lead you to a black and white image. Does that make sense to you guys? Because there's no color information. I can have an equally bright red, equally bright blue, and equally bright green that would register the same on those CCDs. They would look the same level of gray. Okay? To get color information, I have to do some tricks where I actually put little filters on top of these. And I make red, green, and blue pixels. Okay? So effectively what happens is I share information from neighboring pixels, and by knowing the amount of light that hit each pixel, I guess what the pixel value is in color for the one that I have. It's a process called Bayer processing. Those of you that are interested can come talk to me about it later. Happy to talk to you about it. Now, the CCD comes in a huge variety of shapes and forms. Okay, see this kind of blackish part here? That's a square CCD. So that might have 1,000 by 1,000 or 2,000 by 2,000 of those little photodiodes. The CCD comes in, this is your more popular camera format. Okay? Though most of your cameras have ones about this size. And the more expensive the camera, the bigger the CCD, by the way. Okay? Why do you think a bigger CCD would be more desirable? Have any thoughts? Any intuitive thoughts about that? Yes.
Resolution.
What if I say that there's the same number of dots, just they're smaller in the little one and they're bigger in the bigger one?
They can be more sensitive to light.
Yeah, so if I have 1,000 pixels across in this one and 1,000 pixels across in this one, each individual pixel here is going to be more sensitive to light because it has more of a surface area in which to capture light. That's why the cameras, the more expensive cameras that have bigger CCDs, are better at low light conditions. They have less noise. Okay? Now, there's also CCDs that look like this, just a strip, a single linear strip. And actually, in the spectrophotometer that you guys are going to be using, that's the kind of CCD that's in there. It's a linear strip. It's basically 4,096 little photodiodes all in a line. Okay? Just running straight down. So I don't need a camera type sensor in there. I don't need a two-dimensional sensor. I just need the one strip. So these are more like your fancy cameras. Okay? Now, we use all kinds of different configurations because we have all kinds of different needs. If we connect it to a microscope, if we connect it to a spectrophotometer, if we connect it to a small digital camera, a large digital camera. So there's a whole range of CCDs. But before we talk more about CCDs, I want you guys to think about this. This is an aside on digitization, because this used to be common to learn about digitization in high school. How many of you have learned about digitizing information? Yeah, it's pretty uncommon now. Usually it's when you kind of do it on your own or you happen to have a computer class or some other class that teaches you some of this. So I just want to give you a brief aside so you guys have a sense of what this means. So here's a scenario. You have a 1 mile long fiber optic cable. Remember those orange cables I brought the other day? Okay, you have a 1 mile long one of those and a light source. How do you send the person at the other end a message? How might you send the message 1011?
On, on.
So what does that mean?
Flashes.
Type of flashes. You guys understand that? So you might decide that a 1 is a flash and a 0 is no flash. Would you have to have any kind of rules about that?
Predetermined spacing between.
Predetermined spacing. How would you send 17? Does everyone know what that means? Convert it to binary into the same thing? How many of you know what that means? Okay. Don't worry if you don't. We'll talk about that briefly. What would you do with 124, 234? Same thing? Okay. Do you expect it, by the way, to be a shorter number or a longer number converted to binary? Much longer. Much longer. If you're just sending zeros and ones. How would you do capital H and capital I? Huh?
You can do that with binary too.
How?
Assign a certain number to each letter.
Assign a certain number to each letter, whether it's lowercase or uppercase. Sorry?
Morse code.
Morse code. That's perfectly valid. Morse code is perfectly valid. Okay. Hello there. Kind of the same thing. Right? Again, we've just seen ideas. By the way, you guys are the best group ever with these thoughts. I've done this for 5 years, and usually everybody's like has no idea whatsoever. So you guys are doing very well. A picture. Yes.
Pictures and matrix with the colors, right? So each one be a vector, condense it, send it that way.
You guys understand what she's saying? So what would you do? You've got 1,000 by 1,000 pixels in your picture. What might you do?
Start from the left to right, the top row, each pixel assigned.
What would you do for each pixel?
Assign each color a number value.
Assign each color a number value. So what do you mean? Like red is 0 and blue is 1? Or
I think it's typically like they encode each color separately. Like they have a number for green and red and blue. Like different higher numbers mean more of that color.
Okay.
So there's a range of numbers.
So what?
It's like a range of numbers for each color.
Okay. Okay. Sounds good. So the basic idea here is really looking at analog versus digital. Okay. How many of you guys have ever seen a record player? Oh, okay. Wow. Still quite a few. Okay. Did you ever actually listen to it or play it? Or how do you think that works?
The tiny bumps in each groove as the needle tracks across.
So basically, it's a set of valleys. It's like going around in landscapes, if you think about it. It's like, think of it as a little needle that's kind of jumping up and down with the contours of the landscape, okay? Now that contour makes that needle vibrate. That vibration corresponds to the frequencies that you would hear. And so therefore, it's infinitely continuous, meaning there's all ranges of values, and basically every time I play that record, it is slightly different. And over time, the record is wearing down. And when they first came out with these records, they weren't made out of vinyl. They were made out of a different material. I think it might have been acetate. Shellac was one of the original things. And what would happen is it would really degrade quickly. So the first time you hear something, it sounds good. The next time, not so good. You know, you play it the 10th or 15th time, and it's, it just doesn't sounds horrible. Okay. So vinyl was an improvement of that, but still, vinyl records wear down. But they're infinitely continuous. It's hard to repeat exactly. Digital is your CD player or DVD player. That's all digital information. If you ever taken a CD and looked at it in the light in the sun and you see that rainbow pattern, that just comes because of the way the little holes are on there. Because it's all little holes, pits and mirrors, basically. And the closeness of that spacing causes the light to interfere constructively and destructively leading to colors. Anyway, it's similar to the way your spectroscope was working and separating out the colors. You can actually make a spectroscope with a CD as the grading, but anyway, won't worry about that. In this case, they're not infinitely continuous, they're discrete values. That means every single moment of sound in your CD has been changed into a number. Now, by changing into a number, I have to convert, let's see, what do we got? By changing it into a number, I have to convert something that is described by a curve like this of information. I have to divide it into little individual numbers, so I get this stair-stepping effect, okay? So I have to divide it into these values, this. But before, when I had my record, it was like this. It was infinitely smooth. Now, if I have a fancier and fancier DVD player, these steps become smaller and smaller. And the smaller I make those steps, the more closely I reproduce the infinite lines. Yeah. But effectively, if I have a 12-bit system or a 16-bit system or a 24-bit system, it's all dividing it into smaller and smaller chunks so I can better define that number. Yes?
What's a tape?
What is the tape doing? The tape was transferring, I'm trying to remember if it was it digital? I thought it was analog information in the tape too. But how it's encoded.
Is it magnetic?
Yeah, I think all it is a difference in the amount of particles that are moved. So a tape would be more like a record. Now, not DAT tapes. Digital audio tapes were doing the same thing and dividing it up. They were putting a digital signal, but the original cassette tapes were doing what the records do. Now you might say, well,
The old NTEX tapes, I think, were iron oxide particles that were magnetized.
yeah, they were magnetized to a different degree, right, based on the fluctuations. So, and the really old timers had these reels, these big reels, and you'd pop on the reel and you thread it through, and then you attach the other side and you get it started, and then you'd play the music. That was even better because more tape was going through per unit time, so you were getting an even more accurate signal. But again, they had the problem that they would degrade over time. You'd get oxidation, you'd get other things happening to those particles, and the quality would degrade. Okay? So there are still people that say that playing a record, a really good record on a really good record player, is better than playing a CD because it's truer to the sound that was recorded. Okay? And now, with the high resolution DVD players that you can buy, it's hard to tell. I mean, for me, I can't tell, but I also don't listen to these things all the time. Okay? So if we were to convert a number, base 10, you guys already said we can convert them into binary. I just want to show you how that works. If you think of a base 10 number, in the number of 1527, bless you, there are 7 ones, or 7 times 10 to the 0. There are 2 in the tens column, or 2 times 10 to the first, 5 hundredths, or 5 times 10 squared. We don't tend to think of our numbers this way, but this is how our decimal system works. It's a base 10. So all these numbers are to the 0, to the 1, to the 2, to the 3 power. And it just tells you 1527 is like this. And when you add them together, they make 1527. Okay? This is just our base 10 system, just to give you a comparison. When we convert something to binary, if we take this number, 1101, what does that equal to in our decimal system? We can do the same game. We can say there's 1 in the 2 to the 0 column. 2 to the 0 is 1. There's 0 in the 2 to the first column. Notice before we were in the decimal system, so this was a 10 that we were raising to the different powers. Now we're in the binary system, so the number is 2. You can do this for the hexadecimal system. It would be 16. You can do this for the octal system. It would be 8. Would be the number. All of these different number systems exist, and computers use, actually, many of them. So if you were to do all this, you'd come here, it'd be 1 times 2 squared and 1 times 2 cubed. So this number is now equal to 13. So 1101 in binary is equal to 13 in decimal, in our decimal system. So if you were to convert the number 13 into a computer language of on and offs, it would be 1101. That makes sense? You guys see that? Okay. And just to give you a comparison, if you were to look at all the numbers, 0 would be all zeros, 1 would be 0001, 2 becomes 0012, and these are all the numbers from 0 to 15. Okay? And any one digit in a binary system is called a bit. And when you have 8 of them, it's called a byte. Okay? An 8 bits equals a byte. This is showing you only things up to 4 bits. Okay? So the biggest number with 4 bits of information that I can represent is 15, and the smallest number is 0. Okay? So believe it or not, I can represent 2 to the 4th numbers, 16 numbers, from 0 to 15. If I have 8 bits of information, I can represent 2 to the 8th, or 256 numbers, or 0 to 255. And that'll be the one that we'll be talking about a lot, the 8-bit information, because that's how a lot of your images are encoded. Okay? So, now I'm going to give you guys a little quick thing to do. I'm going to give you a 1-bit message that you have to encode and see what it is. Okay, so just get a piece of paper and a pen or pencil. You need a 10 by 10 grid on your paper or pencil, on your paper. And I'm going to give you this code here. This corresponds to the first line. This is the second line, the third line, fourth line, fifth line, sixth line, seventh, eighth, ninth, and 10th lines, with ones being on or black and zeros being off. Okay? You can already see it just by looking at them, you can tell me what it is. But. Sounds like a big cart going by here. Don't worry about making it too precise. Yes, it's 0 blocking. It's up to 0 blocking. 0 blocking. Oh, 0 is what? 1 is blocking. Okay, you guys almost ready? I'll give you another 15 seconds here. Just imagine if your computer was worked at this speed and decoding the black and white images. Or if your digital camera, your 6 megapixel digital camera had to go through. Okay, I'm going to go forward. Sorry if I spoil it for some of you, but there it is. Okay, smiley face. Okay, now your computers are doing way more complex things than this in probably, what, 5 millionths of a second. They're decoding this kind of information. If you think about a video that's doing 30 frames per second, it has to do, you know, something like 720 by 480 or even more of pixels with full color information. So you can imagine what your computer's doing. But how would you send color? Yes?
How long would it have taken, like, one of the original computers to do something like this?
Oh boy, original computers. The original computers didn't use screen output. The original computers used paper output or even punch output. So I'm not even sure. I'm sure just the very fact of having to go across and punching something or drawing it on paper, it could have taken at least 5-10 seconds, I would guess. But I'm not sure, to be honest with you, because they didn't use them for doing these types of things, display functions. They used them for numerical calculations. And this isn't a numerical calculation. This is purely a convert and output. So how would you send red? You guys were talking about it before. What do you guys think you'd do? What's your system?
Assign the value.
Okay, what would you assign red?
I know they're going to have hexadecimal colors. So like the first 2 digits of color red or something, and the second 2 digits become green or blue.
Okay, so you could do, so there's been a lot of different schemes. You guys haven't really been privy to that because you're younger than I am. When I first started, there was green and black, and there was white and black. That's how they did it. So they didn't even have colors. But when we first got color, they were 8-bit colors, which meant that there were some schemes like what you said. You had 8 bits, and you would take 2 bits for red, 2 bits for blue, and 4 bits for green information, or different schemes thereof. And it yielded really splotchy looking images. And there were some tricks that you could do, but you never got true color. So that was 8-bit systems. That was the first big thing that came out with color. The next thing was 16-bit systems. And 16-bit systems is your hexadecimal thing that you're talking about. And in that case, they might use 5, 5, and 6. So 5 for blue, 5 for red, and 6 for green of information. So they would divide the kind of the number and say, you know, you get, what would it be? It would be like 40 values of red, 40 values of blue, and you get 60 values or 80 values of green. And you mix and match by the brightness of each of those. But in our case nowadays, we pretty much use 8 bits for each color. So if we said a strong red is a full, all the red pixels are on, you know, the full intensity, we would say that red is at 255, green is at 0, and blue is at 0. And if you wanted to get blue, all you'd have to do is turn on, if you wanted to get the strongest blue you could get on your display, you'd turn on all the blue. So you'd basically say, you'd have some kind of scheme that said, for this pixel, I'm going to send the red, green, and blue values. And then I'm going to go on to the next pixel and send you the red, green, and blue values. And by doing this, I can represent somewhere on the order of 12 million colors. Okay, so in this scheme of assigning 0 to 255 for each of these red, green, and blue, I can come up with what we call photorealistic images. Huh? Nowadays, they even have schemes that double this, 48 bits. So Photoshop can actually do that. They can assign 16 bits for each, so you'd have 16 numbers here. So you can imagine, now all of a sudden you have 64,000 shades of red, 64,000 shades of blue, and 64,000 shades of green, and that mixture leads to the color, the exact color. Okay? Now, and there's green, no surprise. How would you get this purple? Yes.
Red and blue about lots of times.
So in this particular case, I have red at half intensity, but blue at full intensity. And again, just by varying those, by varying these three values, I can pretty much get all the different colors that we know and love. Okay? Yes?
How would you do black?
How would you do black?
Would you go all black?
How many of you think that to get black, you'd put all of them at full? Raise your hands. Okay. How many of you think that to get black, you'd put all of them at 0? Okay. And some of you just are not thinking about this at all. Okay. So, what's the other thing that could happen? So you know that these are the two extremes. Putting them all on max, putting them all off. What are the two extremes? So you said black. What would be the other extreme? White. Okay. So because this is emission, this is light coming out, if you turn them all on, you get white at max. If you turn them all off, you get black. Okay? So how would you get gray? You basically vary all three of them simultaneously, have them go up in value. So they can go from black to white and process through all the levels of gray. Okay? So there it is, 2 to the 24, 12,777,216 color combinations. And I bet you guys can tell me every single one of them, right? Actually, there is some literature out there that says that women are somewhat better at discerning some of these differences than men. But still not, they can't tell all 12 million. We're very good at discerning differences between two colors that are near each other. But if you had to say absolute, like, oh, that one is 253 red, and 128 blue, and no, you couldn't do it, okay? But looking at variation, we're very, very sensitive at looking at variation. Okay. So what does our CCD see? Okay. So if we take an image of a gecko that I found on a bench in Hawaii, and we look at what the CCD would see if it were looking at it. Remember, now this is just a plain old CCD, no filters in front of it. The plain old CCD would see this. Notice that here it's red and here it's green. I don't really see much of a difference there because the brightness of those values are not all that different. Remember what we talked about before? If I have roughly equal brightness, things are going to look the same. So even this blue, this cyan color here, bluish cyan color here in the eye, looks all uniform, right? Because the brightness of the green compared to that blue isn't there. There isn't information. So what can I do? I can use filters. If I put a red filter in front of the CCD, now all I see will be the red coming through, the amount of red in all of these colors. And look, lo and behold, the red turns out the brightest. And this is relatively bright too, which tells me that there's quite a bit of red in this color. Okay? But now, in the green, like this stripe here, there's almost no red in that green. Okay, you guys see what I'm saying? So there's the red filter. If I try the green filter, everywhere that's green will come through the filter and will show up brighter. So lo and behold, the little tip of the nose here is very bright green, and it's the brightest. And look at this. This is quite bright, which means there's a lot of green in that too. And the body is kind of a medium, but then you've got these yellowish spots. They're actually brighter in green than the rest of the body. And then I can look at the blue-only channel, and now things that are blue will come out through the most. And notice the eye spots come out quite bright. And notice the bench. So that color here has a lot of blue, quite a bit of green, and a little bit of red. Okay? So you guys see, this is what the CCD would see if I were to stick a red filter in front of it that only lets the red through, a blue filter, and a green filter. Okay, you guys get that? Now, is that what you guys do with your digital cameras? You take your picture and then change your filter? No, that'd be kind of hard to catch sports scenes or at a party. You'd be like, hey, let's change the filter. Hold on. No, it wouldn't quite work that way. We do that trick that I told you before, where we put these special sensors, the different colored filters, actually on the adjacent pixels. Now, just to show you, when we use our microscope, the same kind of thing happens, okay? We actually label different parts of our cell with different fluorescent proteins. some that will glow in the green, some in the red, some in the blue. Okay? And then we put the filter on our microscope that only shows us one color or the other. And that's what would happen here. This is the filter that only shows us the blue. This is the filter that only shows us the red. And this is the filter that only shows us the green. So when we're in the lab and we've done all this major work and labeled this cell with fluorescent markers, we come in there and we actually change the filters and we get the image in these different colors. We get this, this, and this. And then we think, that's kind of boring. I don't want it to look out like this. So then we give it the color that it would have appeared had we been able to see it. I mean, sometimes we alter it to make it look a little bit more artistic. And then we get this. And these are the kinds of images you see all the time in magazines that show you cells. And people can play with the colors a little bit to make it look nice as they want. But that's what we get on the microscope, and this is what you end up seeing in the end. Okay? Because the reason we could get a true color image that showed us everything, but we may have one color come out much stronger than the other, things would start disappearing. It would be very hard to take a full color image because the intensities of these might be different. And this way we can kind of match the intensities, match each color, and then get a nice pleasant picture at the end. Okay? Does that make sense? Also, because we are getting images where there's not much light coming from it. Remember, these are fluorescent tags usually. We shine blue light on the sample, or sometimes green light, depending on what the color is coming back, and we get the lower energy color out. It's not ultra efficient, so we don't get a lot of light coming back. So we want the CCD to be as sensitive as possible. And traditionally, a CCD that only sees amount of light is more sensitive than one that has to see full color. Because when you see full color, you don't get as much resolution. You don't get as much true resolution per pixel. Okay? Bless you. Does that make sense? You see how we get these images? And by the way, when we're over at Oak Park at our facility on Wednesday, we can also do fluorescent images of some of your substances. You'll be able to look over there. There's a hot chocolate mix that was done under fluorescence filters that we have down there. It's this thing right here, down here at the bottom. You guys will take a break in a little bit, and then you guys can see what that looks like. Okay? In case you want to try to do something fluorescence related. Okay, the spectrophotometer. Let's go on to our last tool that we want to talk about. And this is one that you're going to be using repeatedly. Okay, you're going to have 2 sessions using this tool. So first of all, just some background. What is spectroscopy? It's really a technique that allows us to analyze samples based on their interactions with energy. In our case, we look at how they interact from near UV light all the way to near infrared light. That's the spectrophotometers that we have. The setups that we have allow us to do that. And we basically look at how do they interact with energy, whether it's absorption that we're looking at or reflection. What's the intensity of photons that are either reflected or transmitted based on energy or wavelength. Okay? And we get what's known as a spectrum. So, why do we use spectroscopy? So, one of the things we use it for is to study something that's way too far away. I want to know something about that star over there. I can't go there and interrogate it. Okay? But I can optically interrogate it. I can see that's a red star, that's a blue star, that's a green star. It has this kind of spectrum, which means it's this kind of a gas, or it's this stage of its life cycle, based on just knowing the color. Okay? The color and the range of colors that are coming from that sample. So astronomical bodies. And I can also study human bodies, eyes, brains, cells. I can study all these things based on how they interact with light. So I can do 2 main things. I can identify components in a sample that I'm studying, and that we call qualitative because it tells us components but not amounts. Or I can do it quantitatively, which allows me to figure out the amount of something in a sample. And I can also, in situations, do both. Certain situations do both. Okay? Common uses. The 400 to 700 nanometers is used a lot in ink manufacturers, use it, printing companies, people who sell textiles. Basically, they can figure out how to match things. So when you want to paint your room because, somebody drew on part of the wall and you want to paint that, but you don't know what color was on the wall, you can actually use colorimetry, which is a simpler form of spectroscopy, figure out exactly what color that is, go to Ace or wherever you want to go, Home Depot, and get the color exactly matched. And the way they do that is they take your sample and they can shine light on it and see exactly what the color combinations are of your sample, and then they can recreate that in the paint that they give you. Okay, so that's how you get the color matching. Now, we can also use it for figuring out ethanol concentration in breath. So if you ever get pulled over, and I hope you don't, for drunk driving, they can make you breathe into this thing, and they can do spectroscopy on the air that's coming out of your mouth, and they can see exactly how much ethanol is in there, in the amount of breath that you've expelled out. And that's how they can figure out if you've been drinking too much. Okay? And paint matching I already told you about. So the big thing about doing spectrophotometry or spectroscopy is that you can look at something, you don't have to touch it to figure out something about it. Okay? So you get to pretty much anything that you want to learn about, you have to interact with it somehow. So the way we interact with things is we take them apart, we touch them, but you can also just have light interact with them and tell you something. So remember, we can do things like, we can look at things like heat, sound, electrical, chemical, photonic, kinetic, and each of these forms of energies you can make interact with the thing that you want to study and figure out what happens to it. So for example, I could, if I want to learn more about this cup, I could heat it in a microwave, get it really hot, and see, do microwaves heat the cup? I could figure out something about the water content in the clay that was used to make this cup. I could blast sound at it, and I make it shatter. Okay, I can figure something out about it. Okay, and in our situation here with spectrophotometry, we're having light interact with it. And again, you saw the profile. And really, this is what we tend to do, is we always plot wavelength times intensity. You can do it by frequency, you can do it in a variety of different ways, but the most common is by a wavelength. So we do that. We have light interact with something. How do we represent the results? That we call a spectrum. And common ways to represent a spectrum are with a picture, counts of photons versus energy, and this is the one that you're going to be seeing the most. Absorption as compared to a standard, transmission compared to a standard, or reflection compared to a standard. And by a standard I mean, if pure white reflects this much light and of these energies, what does my red cloth reflect? That's comparing it to a standard. If my water absorbs this much light, how much does my beer absorb? Okay, the standard was water. I wanted to see the difference between water and beer in the way that it absorbed light. Okay? So these are things that you can do, and actually, some of you may have already done that, like in chemistry labs. Did you ever have to do calibration curves or look amounts of dyes or things like that? Have any of you guys done that? Yeah, some of you guys have done that. That's all spectrophotometry. Okay. So, how do we represent a spectrum? This, you guys remember your NASA spectroscopes? Remember how you saw a little thing on the side with little lines when you looked up at the fluorescent lights? Well, this is, I don't think this one's NASA, but it's a similar agency. They actually had a really, 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 really high resolution one, where each of these lines is showing you the spectrum equivalent of 6 nanometers. So when you guys looked at your scale, that little scale on the side, you were looking at the equivalent of, I think it went from about 350 to about 750. That's what you were looking at. You know, when you saw the rainbow. Okay, so you were looking at some on the order of 300 to 400 nanometers in that space. Well, what they did here is they divided it up, and each line is 6 nanometers. So this is incredibly high resolution. Do you notice there's spots where it's black? See that? That corresponds to something in the molecules of the sun in generating this light. The molecules that were in there absorbed specific energies before the sunlight got to us. Okay? So by looking at this picture and quantifying where all of these are and their intensity, people could figure out what's the chemical composition and what energy states are the molecules in the sun that are generating this light. Okay? Very, very precise. This is more like what we saw. Right? And if you were to go look at the sun, you wouldn't see all those little lines. You would see pretty much a uniform spectrum because we don't have the resolution. This is what we saw when we looked at the fluorescent lights. And you see the spectrum here. It went from 400 to 700. 4,000 to 7,000 angstroms, or 400 to 700 nanometers. So that's what we saw. Well, you can take those things that you see and you can convert them into a graph. And this is already more precise. You guys remember you drew little lines on your paper? This is more accurate. This starts to tell you an intensity of each of those lines. So you could do that. We could take this, and actually I'm doing this process now with iPhones. We're trying to make things like this that you would use in your classroom in high school, middle school or high school. And this would be more like this is a candle flame. And this is supposed to be the hydroxide stretch here. But what kinds of things can I do when I get those spectra? I can measure atomic and molecular energy levels. I can measure geometries, chemical bonds, interactions of molecules. And again, I can do qualitative analysis or I can do quantitative analysis, amounts or components. Okay? Now, what tools do we need to do this? We need a source of energy that we're sampling or that we're using to interact with a sample. And then we need a device that measures this change in energy. So here are our components. To do this, to be able to actually do this, we need a light source, we need mirrors, we need a diffraction grating, which what that does is it separates the light that interacted with our sample into its component colors. We need something that detects how that light has been separated out and a way to interpret the data and display it. So, diffraction gratings can come in the simple little slide variety that you had in your spectroscope. Okay? I don't know if you guys noticed, but there was something you were looking into. That was a little diffraction grating. All that was tiny little lines, incredibly close together. That's all that was. It's kind of like, think of it, a whole bunch of little hairs. Okay? And that allowed the light to be dispersed or separated. This is the one that you would use in a big telescope, like what might happen out on the Hubble. Okay, that very big mirror-like thing that separates out the colors. And a CD does it too. You notice? Red to blue, it separates out light, does the same thing. And then you need the CCD, the detectors that we talked about before. So, how many of you used something that looked like this in high school, a Spec 20? You put your test tube in there, you turn the dial, maybe you were lucky and you had a little digital readout. Depends, I don't know which one you had. Well, this thing right here had a little needle, or the fancier ones had a little number that showed up in red, sometimes even green. And it would show you the amount of light absorption or how much light was transmitted. Well, and this is more like what I used when I was a graduate student. That was a bit more precise, and you had 2 cuvettes. This is what we use now. Okay? This is what you guys will be using too. This little thing right here. Okay? Now, much nicer, easier to use. And let me switch this here so you guys can see this. And you guys we're going to load this software on your machines. Let me put this up here. Okay. So, what does this machine show you? Well, this specific piece of software connects with that spectrophotometer, and it shows me the wavelength and the number of photons that it counts within a given amount of time, in this case 100 milliseconds. So every tenth of a second, it's reading its CCD, its array of pixels, for a tenth of a second and figuring out how many photons did I count of the different energies. And here's the energies, and this one can measure from about 360 all the way up to about 1,000 nanometers. So, with that said, I got a fiber optic attached to it, and if I do this, now I'm pointing it directly at the white on my screen. And what do you see? See those 3 blobs? Okay? So take a look at that, and now take a look at this. Now I'm pointing it at the fluorescent lights. You guys remember what you saw with the fluorescent lights? Remember that you saw lines? This is lines. See that? Can you equate that? Now that's what we see there. And here's what we see with my screen. So what does that tell you about how my screen is lit up? Is it fluorescent lights? What do you guys think it might be? What do you remember that had a pattern that was wider, but still discrete? LEDs. Okay? LEDs had a wider pattern. And what do you guys remember about lasers? Laser. Okay? So you guys will have a chance to relook at a whole bunch of different light sources with these tools and get acquainted with how this tool works. And also observe how it interacts with your skin and some other biological materials. Okay? But this is what we call the Ocean Optics Spectrophotometer. And has about 4,000 different pixels that correspond to all these different wavelengths. Okay? So it separates all the component energies into a given light sample. Any questions about that? Now, what does it look like inside? So this is a little animation that shows you how it works. There's the light, goes into the fiber optic, comes inside, hits a mirror, bounces off a grating, hits another mirror, here's this array, and then it converts into energies. Let me show you that one more time. So notice the light goes in, the fiber optic, and it bends, because it doesn't care about that. Bounces off a mirror, grating that separates into the colors, spreads it out even more, gets the readings on the CCD, which then converts into energies and intensities and counts. Okay? That's what that's what this machine does. And this is what it actually looks like inside if you tear one open. This is the part where the fiber optic goes in. This is the first mirror, slightly angled. Bounces the light here off of a diffraction grating that separates it into its component colors, which then bounces off this mirror, which then hits this strip right here of photodiodes. Okay? That's the 4,096 little pieces that detect light of the different energies. And because you had this diffraction grating that's spread out into the colors, when you get to here, the colors are spread out into the different energies. That thing then sends some information to the backside, which does all of the conversions, and then sends it out to our software via USB, and so we can see the values. Okay? That make sense? So, with that said, we're concluding our look at tools. We saw the laser, fiber optics, microscope eye, and today we added the CCD and the spectrophotometer. Okay? Any questions about those two tools? So that concludes this big picture look. Okay, we've seen all these different components. Okay, so now we're going to take a 5-minute break, and then we're going to come back and I'm going to talk to you about some specifics that relate both to our field trip and to some examples of what we can do in biophotonics. Okay, I would suggest that you take a look at this poster and see some of the things that your fellow classmates have used before to look at. You have a choice of bringing something that you can look at the surface or that you look through. When you look through something, it needs to be really thin. Okay? When you look at the surface of something, it doesn't have to be thin, but the more uniform it is, and times it isn't up and down too much, the more in focus it will be. Okay? If you can be creative and bring some other things, that would be great. So you see there's money, there's leads, there's hair, there's e-mix, there's shaving blades, there's all kinds of different things. Watches. What do you guys think you might bring? We can see things from about 10 times magnification to about 1,000 times.
I don't want to do
Exactly. You could throw something else, that'd be great. That would be helpful for everybody, but I need to have unanimous agreement before I go about it. If one person says no. Would that be something you guys would be interested in? Moving into the last day of class, the final? No canceling stuff. Ordinarily, we have to be Saturday evening.
Last day, right? Yeah.
Yeah, it's like bad time. And it's horrible for people that have to grade them all, have it all in the next day. I know, it's that's the other person said too, so I'll ask. Is it good one here? I will ask that. I would like to move it too. That's the worst. I know, it's a multiple time. You guys have a motion, right?
Literally is the last class of the day. So yeah, it was struggling.
How about you guys? What do you guys think about bringing it? Because the thing is, we have to do it like really fast. Because I have about 2 minutes to get the image of each person's thing. But I can also do it later. You guys can leave me the sample. I can finish it for you. You'll see. Hair is kind of the easiest, but it's kind of boring. I mean, maybe the end of a hair we haven't done, like where it comes out. That we haven't done. Okay, you guys, why don't we get back? So it will be fantastic if we look at things that I haven't looked at before. That will be the best. I want to ask you guys something quick about the final first. We happen to have the last slot in the final series, which is not that much fun. So I've been asked by some of your classmates if we can move the final to the last day of class instead. And we'd be happy to do that, okay? Everyone is here today, so the only thing I need is I'm going to give you today, if any of you object and you don't want to let your other fellow classmates know, then send me an email. Because if we don't have unanimous agreement, then we can't do it, okay? So I will wait the rest of this day, and Wednesday we'll announce it, or if I know sooner, well, I'll wait till the end of the day, and if nobody emails me from this class telling me that they don't like that idea, then we will go ahead and move it, okay? But I'll confirm that on Wednesday.
If we didn't take the final on the last day of class, what would we have done? Could we review information or something on the last day of class? Or?
I will accommodate the schedule. You'll still get the full review period. I'm not going to change that. It just means that I have to take one speaker less.
So what day would be the last day?
What is it? I can't remember.
March 16th.
I think it's 15th. I have this idea of a 15th.
March 15th would be the last day of instruction.
Yeah.
That Monday.
And that's a Monday. So we would have it on that Monday instead of doing it on, I think it's the 20th.
That will be Saturday the 20th, 8th, 16th.
Yeah. And then I have to have the grades in them right away the next morning. Okay? So if I don't hear otherwise from you guys today, please feel free to email me with any concerns that you might have about moving this time. We will still have a full review session. Don't worry. And I won't cram in extra stuff. I can adjust. We've had to do these kinds of adjustments before. It's not a problem. Okay? But if you have any objections, let me know, and then we will go back to Saturday. Okay? Everyone understood that? Because you're all here based on the rule. Okay? So just let me know if you don't like that idea. Okay. So what I want to do now is I want to give you an overview of some of the CBST biophotonics projects and also some other examples of biophotonics research, just to prime you for your visit on Wednesday, okay? Feel free to interrupt me, ask questions about it. What happens on Wednesday, just for you guys to know, is we will have you meet out there by, you know where the parking structure is? The multi-tiered parking structure near the buses. I guess it's like right out there.
Yeah.
We'll have you meet, I think it's on that corner by the parking structure, so we don't interrupt the bus parking here, but we still have you over there. Probably Professor Shackelford or Elisa Lee, who as an administrative assistant, will be there waiting for you, but probably it'll be Jim.
Yeah, leave as close as we can to 10 o'clock.
Close as you can to 10 o'clock.
Enrollment check, make sure everybody's there, and we'll head right out.
So it's very important that you're there at 10 so we can head out. You'll get to us probably a little bit before 10:30. You'll have about an hour at the facility, which will be you'll be divided into two groups. One group will get a 25-minute tour, and then it'll switch, while the other group is getting images of their materials and also working with some of the other materials that are out there. There'll be the infrared camera. You can draw on yourself. You can do all kinds of different things. But you'll get to experience some of those tools, and then there'll also be the tour, okay? And there'll be the taking of the images. Please make sure to bring your samples and any kind of sample preparation that you need. I do have microscopy slides, so don't worry about that. We'll have that for you, and we'll try as much as we can to get your samples taken. You'll have some simpler microscopes that you guys can look at your samples so you can tell me what you want imaged. And then we'll have time for probably half or two-thirds of you to take the images while you're right there, and then the others I'll have to finish after you guys leave, because it's just very quick. You will be back by 12 or a few minutes earlier, so it's exactly the class time. Okay? Okay. So, first to give you, yes?
Would we have anything to do with the staining stuff? Like if we can do the stain, we could actually do it?
No. But we can do transmission microscopy, we can do reflection microscopy, we can do dark field, and we can do phase. So dark field and phase allow you to see things that are normally transparent pretty readily. So we've looked at water bears, which are these little things in your water supply when you go to a pond or something. Not water supply, when you go to the pond and you grab water. There are these little things called water bears that swim around, and they're transparent, but they look great in dark field. Dark field, remember, is when we make the background all dark and we make the thing that we're looking at light up. You look at the light that's hitting from the sides and reflecting. And we also have polarized microscopy, which is really good for very regular type of things that are transparent, and it shows lots of colors. And we also can do phase, polar, and we can do fluorescence. And now fluorescence, typically those are living materials will fluoresce, tend to fluoresce, and also some other things fluoresce. You know, somebody told me about their watch band or some other paints. Those can also fluoresce. Okay, so this is the building you'll be going to, and it's at the medical center. I don't know how many of you guys know, but UC Davis has a main campus and then it has a medical campus. Okay, there are some medical students that do some of their work on the far edge of campus here and then transfer over there for more clinical work, but a lot of the places are right around where you're going to be on Wednesday. We are one of 17 science and technology centers funded by the National Science Foundation, so your tax dollars and mine, very, very small, teensy-weensy fraction, goes to funding national science research, and even smaller fraction goes into education. Okay, so I work with the education fraction of our center, but I also work with all the scientists that work within the center, and you'll be going to where our primary facility is. So this is where the primary instrumentation is for our group. This is just a sampling of where science and technology centers have been, and the ones that are triangles are ones that are active right now. The reason why I want you to be aware of this is because if any of you are interested in doing research, which if you're interested in science, engineering, technology degrees, I highly, highly recommend that you do some kind of summer research. Highly, highly recommend it. You can already do it. We've had quite a few ISTLA students do research between their freshman and sophomore years and then go on to continue doing research. It's very important to do if you're leaning in those directions for career, because you'll figure out if this is what you like. You'll also get a sense of which area you like, okay? I've known people that have hopped from area to area to area to area doing research and then finally find something. I've seen people that try one and say, I'm never going to do this again. I'm going to go into business or English or whatever, you know? I've seen everything, but the important thing is for you to figure out what it is that motivates you to do your best, okay? Because when all is said and done, If you do something you love, you're going to do it a lot better than if you do something you don't like very much. Period. There's no ifs, ands, or buts about that. So it's good to get experience. To give you a sense, in our center, we have all of these different institutions involved, including Stanford, Alabama, University of Texas San Antonio, Mills College, which is an all-women's college in the Bay Area, Fisk University in Tennessee, Berkeley, UC San Francisco, and Lawrence Livermore National Laboratories. Primarily, our students that do research end up being either at Lawrence Livermore or at UC Davis, with the majority being at UC Davis, either campus or medical center. So if biophotonics is the type of thing you like, you should talk to me and we can try to figure out if we can put you in a research project, either over the summer or during the school year. If you're interested in some other topics, all these other centers, I know many of them, and they do things like marine ecology, they do earth surface dynamics, they do polar ice sensing, they do space weather, okay? They're all kind of the lead, space weather is actually a really big deal, believe it or not. It's these solar flares that come from the sun, and they can emit so much electromagnetic energy that they could take out all of our satellites. Or they can cause power transformers to go on the fritz. I mean, there's all kinds of things that can happen. So it's actually a big deal. I went to the place in Colorado where they monitor this, and they're always waiting for the big one. I hope we don't have a big one.
Didn't it cause, like, the northern lights to come all the way
Yep.
down to the north to the United States?
Yep, they cause northern lights. Yep. Those storms cause northern lights too. Yep. You know what that is? Where the sky glows at night, different colors, the ionosphere. And that's photons of different energies coming in and interacting with the particles in the ionosphere and causing that glowing. But there are many, many different centers, and all of them have some kind of undergraduate research experience. They usually pay you. They put you, some of them have housing, it varies. But if you like any of those topics, these are some of the leading places to get this experience, and you get to meet a lot of different people. So it's a nice exposure. If you guys want to go into engineering or science, there's ones focused very heavily on engineering. If you want to go into any of these areas, it's a really great opportunity for you to get a broad range of experiences quickly and get paid for it. They are competitive. Like ours takes about 30 students and we get about 150 to 160 applicants. So just so you know, something to keep in mind, always ask me if you're interested. I can point you in the right direction. This is the building that you're going to be coming to. Gives you a sense of what you're going to be, the kinds of facilities you're going to be seeing. Biochemistry lab, this is more of a microscope lab. This is the layout of the building, and you'll be coming in this area right here. But we have a big educational outreach laboratory here where you'll be getting your samples, images of your samples, and then you'll be getting a tour of these laboratories over here. The nonlinear microscopy lab, single molecule spectroscopy lab, and advanced imaging labs. Okay. Now, what happens in a center like ours, specifically in ours? What you see is that we make a lot of biophotonics tools. Not a big surprise. We're the Center for Biophotonics. We make biophotonics tools. They tend to vary in the area of medical, advanced imaging, and spectroscopy. Again, spectroscopy. What was spectroscopy? Sure. Who was it? Generating a spectrum showing you what?
How material interacts with energy.
Yeah, exactly. Looking at the interaction of energy and showing you that in some kind of visual representation. And then we have an area that's molecular and cellular. Now, we apply these things and work on problems that have to do with infectious disease, neurological disease and trauma, vascular disease. We work with industry, biosecurity, basic research, agriculture, biotechnology, cancer, and regenerative medicine, so the stem cells, things of that nature. We work with people that have problems in these areas, and we apply our tools and techniques for these areas into those things, to those topics, okay? So that's the range of things that we end up working on, that our scientists end up working on. And our core competencies are here in making these tools and in figuring out how to then work with doctors and other researchers to make them apply to their field. We have about 120 PhD and MD faculty and staff researchers, okay, that are involved with us. We end up having, right now, about 25 graduate students full-time and about 108 graduate and undergraduate students part-time working with us in one way or another. And we roughly have a base operating budget of about $5 million a year, okay, for doing all the science. And I know that sounds like a big number. It goes very quickly. You'd be surprised how quickly it goes. University takes a third of it right off the bat, just for keeping the lights on and doing things like that, okay, and the rent of the building and stuff like that. But We currently have about 21 projects, and you'll be seeing some primary ones. So, imaging tools. You guys remember the HIV video? You're actually going to get the graduate student that did this work is going to come talk to you about more of the specifics of that project. He'll be giving you a talk next week. But I don't know if you guys remember when Dennis Matthews, the director, came, he showed you a video of plaques inside of an artery. There was like fly through an artery with a stent at the beginning. You know, those are the kinds of tools that we can make that allow you to image inside the human body. And this is a forearm where we're imaging where the veins are by just using near-infrared radiation. We also have sensors and assays. I'll be giving you specific examples of these in a moment. And we have clinical diagnostics and therapy. Okay? So I'm going to show you some examples. I'll tell you which ones you'll actually have a chance to see in greater depth when you get to the center, and which ones are not necessarily affiliated with us, but I thought might be relevant and interesting to you guys. So let me see if I can stop this for a second. The first one I want to show you is something that we have been involved with from the beginning, and it involves trying to figure out the structure of proteins in 3 dimensions. Okay? You guys ever seen molecular models of proteins? Albumin, maybe hemoglobin. You guys have seen some of those things? How many of you have gotten to see that? Like with a molecular viewer or images? One of you. Okay. Okay. So, a lot of people spend a lot of their life trying to understand the 3-dimensional structure of a protein or of a set of proteins. Why? Because sometimes the making of a protein causes a problem. Alzheimer's disease. You get these protein plaques. Oops. Why did one go by itself? This one thing still has a timer thing on it. You get these protein plaques that you don't want to build up. So if you know something about their structure, you might be able to target something at them. Okay? But unfortunately, the way that we currently get protein structures is we use a lot of undergraduate and graduate student lifetimes to crystallize these things. We try to make a crystal of them. And when we get a crystal of it that's good enough, we shine X-rays on the crystal and we look at the pattern that these X-rays are scattered in. And based on that pattern, we use mathematical equations and modeling to figure out what molecular structure in this crystal would have led to this pattern. Okay? Unfortunately, 90% of our proteins don't crystallize. So when I was in graduate school, I had plenty of friends. Come on. I had plenty of friends that literally spent 2-3 years with lots of little glass containers, with lots of little solutions, with protein in there, and this one more salt, this one less salt, this one a different pH, all these different changes, and they might have 100 of these, and they put them somewhere where they thought was going to be really still, because you don't want any vibration, you want the crystal to grow without vibrating, and they'd just wait. They'd come back a week later. Okay, has it changed? No. They'd come back. Oh, I got one. It's coming. It's growing. Okay, in 3 months I'll be able to come and get it and do something with it. Okay, and they'd be all excited. They'd take that thing, they'd put it in the X-ray beam, and the pattern would be garbage. And in the action of doing the pattern, they would destroy their sample. So you got to start over. That crystal didn't work. Somebody breathed over it while it was growing, or we had a minor earthquake and it messed it up. Okay. Every once in a while, they'd get one that had the right pattern, that was good enough, it was pure enough, that crystal, because the big deal here is to get it really pure, really repeating, because that's how you're getting the information, from a very, very repeating structure. And they'd get the pattern, and then they could do the calculations over the span of a few months, and they could have the 3-dimensional structure, and that would be their paper and their thesis, and they'd be all excited. But many, many more were disappointed because they never got to something that was good enough to show levels at the atomic scale. So, what is this project that I want to show you? Well, this is one heck of a long tunnel where they generate incredibly intensely strong X-ray beams. If you want to think about a laser beam, it doesn't matter, but a beam. Okay, X-ray beams from what's called the LCLS, the Linear Coherent Light Source. It's something that they've been working on for years to build because it's underground. It's one of those gigantic, multi-mile tunnels underground. that creates really high energy X-rays. And why do they want to do that? Because they want to shoot these at individual protein molecules. Not crystals, but individual protein molecules. That we can get for every single protein. We have no problem getting that. The problem is getting the crystal. So what they want to do is, why do they need this really ultra bright X-ray source? Because from each protein molecule, they want to shoot the X-ray at it, blast the heck out of this protein, but in the meantime, do it so quickly that they get a pattern. Pattern's really noisy, but if they do this 100,000, 200,000, 1,000,000 times, so one protein molecule, shoot it, one protein molecule, shoot it, one protein molecule, get the pattern, they can get a good enough pattern, they can get the three-dimensional structure of this protein. So they've been working on this since we started, even before that, so it's been going on at least 10 years, working out the math for this, because when you put the protein in, it can be in different orientations, so it's not quite like a crystal where everything's the same. Working out the math, and then also making the machine. So now it looks like it works. And it looks like now they're starting to be able to do the test with proteins. And this is a video that shows you that process. So there are the X-rays coming down the long tunnel, coming into a room where there's this thing, the target chamber. Uh-oh, just lost the button. And in the target chamber, there's the beam. And the beam comes in. See, there's the beam and the protein are coming at the same time, and it's giving you a pattern. And you add up all those patterns of the X-rays hitting the protein, and you get more and more and more of these patterns. And then you can take that information, and you get the pattern of the protein from all these different angles. And then mathematically, you can convert that into a protein structure. Yes?
So where is this tunnel? Or is it?
They were doing it at Stanford. Come on, just want to keep going. Okay, so to give you a sense again, by the way, this is looking down the tunnel inside the actual machine, and this is the actual target chamber when all the action happens. Okay, it's a picture of it. It's about, not too big. Like this, about like this. And this you can see is a long tunnel where the beam is being generated. And the idea is just you needed to have a strong enough beam. That's the big idea. And that's why it's taken so long to get that. Okay? So the big deal here is that we can now work on the other 90% of the proteins, which a lot of them are surface proteins on membranes, which are very important for things like AIDS, lots of the diseases. We can start to look at trying to get a three-dimensional structure of them. Okay? Does that make sense? Okay. So if any of you want to go in that area, it's hot and just beginning. It's a growth area. Oops. Why is this here? Okay. Another thing that we do now, that machine is not at our center. You're not going to see that in the basement. It doesn't quite work that way. But you will see this. We have a machine that does what's known as deconvolution microscopy. So the very best optical microscopes give you things that are in the 300 to 400 nanometer resolution range. And we have something called a deconvolution microscope, which extends that and lets you get down to about 250 nanometers of resolution. And the way it does that is it says, if I've got something with fluorescent markers, that's, when I excite it, it's giving me light back, I know that those are point sources of light. And even though it looks like a blob, when I look at it under the microscope, I can use some mathematics to go from the blob back to the sharp point of light. And what that looks like is this. If I see this under the microscope, but I know that this is a fluorescently labeled product, and I can do this deconvolution, I get this. Or I go from that to this. Or if you were to look at an image that's not a microscopy image, I'd go from that to that, just to give you a sense. Because I know that the light is coming and has certain behaviors where it's coming from, and I can actually reconstruct it mathematically to give me a higher resolution image. Now, if I wanted to take a movie of this, I'd have to collect all the images and then do the processing, and then I'd get to see it. I wouldn't see it in real time. Okay? But this deconvolution process takes advantage of the fact if you know the kinds of light sources that you're imaging, like little fluorescent molecules, I can recomposite them mathematically into a sharp image. So you will see this microscope, and this is an example image that we got from this microscope where you see rat neurons in red and astrocytes. So you can see images that before you would never get this clearly. You can see, and he has a big poster that shows you this one. You'll be able to see that image. And you'll see this microscope. This is one of our graduate students, Greg McNerney, who will actually be coming to talk to you about the HIV project, because he was the one that also did the imaging in the HIV project. Now, if you want to go even higher resolution, we have this technique, the super resolution structured illumination microscopy. Now you're in this range, the 50 to 120 nanometers of resolution. So you can see objects that are really incredibly small and still alive. Okay? And this is the one that I was telling you about, where you get more array patterns, you shine light onto the sample, and you rotate it, and you see what it does, and how it changes the pattern underneath. And by doing that, you can see fine detail at higher resolution, because the small details are amplified by the interaction of the light pattern on top of the sample. So if you apply that to something real, well, in this case, 50 nanometer fluorescent beads, this is what they first tried out with, then this is what you would see under the best conventional microscope, and this is what you see with this technique. You start to see the little tiny fluorescent beads that are 50 nanometers in size. Okay? So this you will be seeing is this is the instrument I was telling you about. It's the highest, the world's highest resolution microscope, optical microscope that is commercially available, and we worked with a company to make it. So you will see this device, and this just shows you some real things like actin filaments. That's the difference. This was the beads that you saw before, and this is the anaphase chromosome images. You can see the very best conventional and what the structural illumination gives you. And this microscope has been used to image that contact point between the HIV-infected cell and the non-HIV cell. And this just shows you some other things you can do. Believe it or not, this machine actually has the deconvolution microscope, and then it has a super high resolution. It's all like one continuous unit. And this shows you, if you take an image, first with the deconvolution images, then you look at an area of interest. And these, by the way, are liver, sinusoidal, and endothelial cells. So they're basically the capillary cells, the covering cells of the capillaries inside your liver. Okay? We can look at that region and blow it up. This is what you would see under the convolution microscope. And you look and you say, you look under this microscope and you say, this is something weird. I wonder what that is. Then you can go ahead and go on the structural illumination, and this is the same thing with that super high resolution, with the pattern on top of light. And you look at that same region that you blow up, and you start to see these little holes, and those are called windows. Okay? It's a sieve plate. Fenestrae is what they call them. But they're windows that show you a way that the capillaries can have leakage. Okay? So this is a way that you can study these things in these cells, whereas before, even with deconvolution that gets you better resolution than a regular optical microscope, you see this. You can't tell that there are discrete holes in them. But now that we have the higher resolution microscopy with the structural illumination, you can actually see the holes in them. Okay? So this is opening up a whole new area of biology, because before, what we used to have to do is if we wanted to get that kind of information, we'd have to put one of these samples into an electron microscope. And you guys know what electron microscopes do? You've seen those images? You've seen the bugs probably, 3D bugs and stuff like that. Well, you can also do it cellular type imaging, but the problem is you have to coat your material with platinum or gold, and that makes them not very lively. Okay? That makes them altered from what they are when they're alive. Whereas in here, we can still do it with something living. We still can't do this ultra fast. It's still, I think the best we can get is about a frame or two per second. But we'll have to ask them that question tomorrow, how fast they've gotten it. But the idea is to make it video rate, because ideally we'd see processes happening in living cells in real time. That would be the goal. Okay? Now, an example of sensors and assays. Sensors and assays. This is where we trap the cell. You guys remember me talking about this? You can use a laser to trap a cell. You will see this microscope there too. We call this the R2D2. It's an automated microscope that can do a lot of this work by itself. You can find cells in its field, grab them, and actually take a spectrum of them. What we do here is you can see the blood cells. Here's the laser. There's a blood cell. It got grabbed and it got pushed over here in this container over here. Let's see if we grab another one. That's the laser beam right there. Boom, there it goes. It grabbed a blood cell, bins it over here. Now it's going to grab another one. It missed. It missed. Ah, there's one coming. Grabs it. Oh, ended up pushing two over. Okay? So what this can do, not only can it grab cells and move them, this is a continuously flowing system that allows you to bin things. But when it's grabbed something, it can do something called a Raman spectrum. It can look at how energy interacts with that cell and generate something that looks like this. And you guys see how there's two different spectra there? One of them is a cell that's healthy and the other one is a cell that's cancerous. Or one of them is a certain type of stem cell and the other one's another type of stem cell. There's signatures that cells have based on what their constituents are in the cell. And cells that are cancerous tend to be more active, so they tend to have more genetic material, for example. And so they would show up as different. So we can look for those differences and actually segregate cells based on their properties in Raman spectroscopy. And Raman spectroscopy is different than just the light that's absorbed or the light that's reflected. It's how energy is added or subtracted in ways that do not correspond to specific energy levels, but it does relate to the vibration of the specific molecules. So you will be seeing that. You'll also be seeing this. This unit right here is called CARS, Correlated Anti-Stokes Raman Spectroscopy. So again, it's using this technique of Raman spectroscopy, which you'll be hearing more about. But what this allows you to do is it allows you to image things within cells without having to put labels. Okay? People complain about having to put labels, one, because it's a pain in the butt to put labels on things, but also they complain about it because they say, I'm trying to study something this big and the label I'm sticking on it is this big. I think I'm going to alter the behavior of the thing that's this big. And it's a fair concern. So in this technique, you can get two-dimensional images and eventually even three-dimensional images without the need of labeling. So you're looking at something intrinsic, like you're looking at fats, like lipids. In this case, they looked at monocytes, so fat cells. So they figured out where the lipid vesicles were, the little blobs of fat were, because they could image it directly. In our regular microscope images, you wouldn't see these. You couldn't make those out as being separate. But with this technique, you can figure out where these points are. This is kind of showing you how it looks at the signal. And then it shows you where the lipid globules are, the little fat drops are. And the technique is very good for looking at certain things like this. So you'll be seeing that. This is going back and showing you that when you do these laser trap measurements and you get a spectrum, you can then, based on that spectrum, you can group things. Normal cells versus stem cells, or in this case, you can image drug-resistant bacteria and see what's happening, which E. coli are resistant, which E. coli are not. And you can do that ahead of time. So the idea, for example, with this experiment is that you would like to know if you've got a certain sample of E. coli that are problematic, because not all E. coli are nice. Some E. coli can kill you. You want to know what kind you have so you can figure out and match the antibiotic. This is a way you can query those cells and figure out under which population they belong and where they are in their phase of growth. So again, you're querying the cell, and based on the kind of light interaction you get with it, you find out something about the cell. When we get to clinical, in clinical scenarios, this one was one that I was showing you. This is a brain surgery going on right here. This is someone's brain. They've cut out the bone here and taken that plate off. And they're going in, they're trying to remove some kind of tumor. And the way that they're trying to figure out, see, it all looks pretty similar to me, and it does to the surgeon too. And they need to figure out which parts of the brain need to be removed. So they have this little tiny probe you can see here in the surgeon's hands. And that probe you touch to the top of the part of the brain that you're trying to image. And light goes in, it shines around the tissue and some light comes back in the receiving fiber. And you can look at, here's the wavelength, and here's the intensity of light. So this is the fluorescent diagnostic signature. So you shine a certain color of light in, and you look at the light that comes back. And if you have normal cortex, normal brain, you get this pattern of energy, intensity coming back. But if you have a low-grade glioma or a type of tumor, you get this type of a pattern coming back. So based on it, you know that at that point, you know whether it's cancerous or non-cancerous tissue that's causing the fluorescence to come back. Okay? So with that, you would know where to go and cut. You'd have a better sense of where to cut, even though it all looks the same to you visually. And you can also, instead of doing just the fluorescence that comes back, you can do fluorescence decay. You can look at how quickly after you turn the light off does the light go away from the fluorescence. And this shows you that the normal versus the low-grade glioma do have different profiles and how quickly the fluorescence decays. Question about that? This you will not be seeing. We're not going to go in for brain surgery. This, I may have one set up. This is showing you how we can take an iPhone and we can convert it into a microscope and get images. These are images of blood, for example. We can do it very, very simply. We can also take the iPhone and convert it into a spectrophotometer. So giving you the spectra, wavelength versus intensity of different things. Not as accurate as this device right here, but still quite usable. Okay? So that'll be something that, it's actually something I'm working on right now. I'm trying to make it cost like $2. So I'm using toilet paper rolls and different easy things to use for this tube. And it's actually working out pretty well. So these are devices we're trying to get so that we can bring this into the schools. Something this is not CBST. CBST shows you that you can look at things that are happening in the body based on the heat signature, how the heat is distributed among the body. And this is showing you a person that's, you see how symmetrical they are? This person's doing relatively well. They've got a little extra heat on this arm, so something might be, their muscle might be inflamed or a little overworked. But you can use it for quite a few things. So here's what a sinus headache would look like. So if you do very, very accurate imaging, you can actually see where there's congestion because the temperature is elevated. Okay? You can look at back pain and where it's localized because you get, this is a lower back, this is in the middle, this is lower with a few different points. And those could specifically be certain vertebrae that are impinging in some way or very close to the skin. This is lower back. You can also look for carotid artery inflammation, things over here. So things that are relatively to the surface, you can actually see based on the temperature, and you can also look at oral pathologies. So these are some problems that this person has with their mouth. Okay? So again, you're looking normally for a healthy human being to be relatively symmetrical. When you don't see that symmetry after they've been equilibrated in a room, I mean, because if you take off your shirt and you look at your arm, there's going to be a line right here. That doesn't mean I have something wrong with me. It just means that this was warmer than this. But if I have my body equilibrate and then I take an image with a very high resolution camera, I can see these small variations. And this can also be used for imaging of breast cancers. So this has been used for this. And you can see, you can even monitor here what's happening is this IBC, this is not the same person, but you can see an inflammatory breast cancer. And then you can see here, after it's treated with a certain drug, that it goes away. And you can kind of tell that it's on the way to being cured. And in this scenario, this is healthy, normal. And you can see this is a ductal carcinoma, a cancer here. This is fibrocystic changes. So you see that you get lack of symmetry. And that lack of symmetry, that change, shows you what's going on. The other one I wanted to show you was the diffuse optical imaging. Remember I told you about I can put lights into the, I can put lights on a pad, different lights, and I can shine it on the brain, and I can see how the light comes through, and it comes out in a banana shape. I don't know if I ever told you guys about this. I can't remember. Well, I can create this cap. This is a fancy one with 32 fibers that put in light and come out. And the way light goes and travels in your brain is it goes in and it comes out roughly in a banana shape, all the way around where the light went in. Okay? So I can put a detector, depending on what depth of penetration I want in your brain, I can put the detector slightly different places. And if I put it in the right place, I can get a pretty good signal. And I can effectively do, you guys remember the pulse oximeter that we put on your finger and it showed you how much oxygen was in your blood? Well, I can do the same thing with your brain. I can look at how much oxygen is in that path, how oxygenated it is. And our brain, when it's working, more blood flows to the area that's doing the processing. Okay, that's how functional magnetic resonance imaging works, variety of these different techniques. But I can do it just with light and get a pattern kind of like this, and I can see that this part of the brain, here's a person's head from the top, this part is more active than this part. And I could do this and actually see where the activity is, and this ends up being used with very small infants or premature infants, partially because their skull is very thin, it's very easy to have the light penetrate. I can get pretty deep penetration, I could even get more than a centimeter. And this is what the machine looks like, and it comes with this little paddle, and this little paddle has 8 or 16 different lights and sensors in there, and it can in real time image, in a sense, in kind of a rough way, the blood flow. So I can see if that part of the brain is activated. I can make a loud sound, or I can expose to light, and I can see if different parts of the brain activate. Okay? And it's non-invasive. Again, I can do it very easily just by placing this thing on the head. And this can also be used for scanning for breast cancer. A lot of these techniques have been used for things like this because anything that's more superficial is closer to the outside of your skin. It's easier to do with these techniques. So it's also been used there. And you can get patterns that look like this. Here's the cancer pattern at the different wavelengths, and here's the normal. So I can kind of have this light interacting with the tissue, and as long as it's not too deep, the thing that I'm looking at, I can actually get a sense of it just by looking at light interactions. So in summary, there are these 3 different types of things that we do at CBST: imaging tools, sensors and assays, and clinical diagnostics and therapy. And you'll be seeing primarily examples from imaging and sensors and assays when you guys are there. Okay, with that said, any questions about that, those examples? I know it was kind of a whirlwind. You got a general idea. So what's happening? We've got the tour, 10 a.m. bus or parking structure. Send email in case you have any questions. Bring a sample to take an image of, and we already told you about that. This Friday, I need to meet with your group leaders for your presentations. And I wanted to have a quick show of hands. Is 10 o'clock better or 11 o'clock better? How many groups can have at least one person from your group come at 10? Okay, so I see 4 groups. There should be 6 groups in here. I've only received information from 4 of the groups. There's still 2 groups that are not formed. So it looks like the 4 that sent me information are the ones that raise their hands. How about
I didn't raise my hand.
Oh, okay.
But I can hear you.
You did, okay.
So 11 would be better.
So how about 11? Which of you can make 11? So we've got the same, no, are you raising your hand? How many of you can make 11? Raise those hands. 1, 2, 3, 4, 5. 5 groups. Can the one group that didn't raise their hand send somebody at 11? Doesn't have to be your group leader, but send somebody. I don't know since I don't know the other 2 groups, I don't know who it would be. Well, let's aim for 11. Make sure to send me information about your groups if you haven't already done so. Okay? Okay? And I'll look at the names and I'll try to send the people who haven't gotten into your group, I'll send you an email to remind you. Okay? So we'll say 11 o'clock on Friday. I need to meet with all the group leaders and we're going to start discussing specifics, formats, things that are available to you, discussing your ideas. Okay? This will now happen for the rest of this month. We will be meeting on Fridays at 11 to discuss this. Okay? Be aware. It doesn't have to be the same person that comes. You don't necessarily have to come to every single time, but it's important that you come to these first 2 meetings. Are going to be really important because that's where things get set. On the 9th, we'll do bioluminescence of plants and use of fluorescent markers. This will be the graduate student talking about HIV. And then on the 10th and 17th, we're going to be using the fiber optic spectrophotometers. So we will be needing your computers on these days. At least 1 computer per group.
Is that recommended on Tuesday?
Oh. No. Okay, I must have made a mistake here. This must be the 8th?
Yeah.
This must be the 8th, sorry, just making sense. Okay? Okay, so everyone know where you're coming, right? Wednesday, over there? And Professor Shackelford will be there. Please be prompt. Make life a lot easier. Because we can't really wait. Okay? Okay, see you guys.